play out their lives and die and recycle. And you can say that if you boil down Lotka's idea, it's basically the idea of that, well, you have a dynamical system described by differential equations with state variables, x1, x2, whatever, and each of them have a dynamical equation, so that the rate of change is determined by the state of itself and all the others. But what Lotka also brought into this was this, and that's sort of a physical chemistry link, turns out, that you can different types of units. It could be cells per milliliter, or grams carbon per square meter, or micromoles of nitrogen per cubic meter, or something like that. And still there would be some elements that would be contained in these organisms that would have to be conserved, because that's sort of one of the few hard laws we actually have in biology, the conservation laws of mass, of elements. So, Lotka's stoichiometric constraints basically say that for each state variable there is a conversion coefficient, which would be sort of, let's say if the element in question is phosphorus, then it would be amount of phosphorus per unit of x, and there would be one of these stoichiometric linking coefficients for each state variable. And as we have heard before several of sort of modeling model types earlier today, people usually assume that these are constants. For example, the good old Redfield ratio. And what we will try to do here today is to see what fun or hell breaks loose if you try to play with non-constant stoichiometric linking coefficients. So yeah, I mean, as I said, we wrote some papers in the early 90s. This was sort of part of the inspiration that led to this book that came out in 2000, I think, by two Americans, Bob Sterner and Jim Hudson. And they sort of took this simple idea of that organisms are basically made of the same stuff, put it together systematically and try to sort of see how far can you take this, how far can you take these almost trivial facts and find something meaningful out of it. So one way of defining ecological stoichiometry is sort of the balance of energy and chemical elements in biological systems. And we can see how this can affect competition between, for example, herbivores or producers, how it can affect the herbivore-producer linkage, and how this linkage here has serious consequences for how food webs function, how efficient they are, how they process materials, and how that, again, relates to biogeochemistry of, let's say, on the ecosystem scale. How much material flows this way and how much flows that way. This is just one more or less arbitrary figure from the book, but it's saying it just lists different types of cellular organelles in terms of their P content and N content. And we see that there is a huge variability in how much P you need in relation to N to build different of the, let's say, building components of all living systems. And we especially notice that Jim is professor at Arizona State University, Tempe, Arizona. In 2000, there was a group of people who got gathered in this place in Santa Barbara called the National Center of Ecological Analysis and Synthesis, and just compiled a bunch of very simple measurements of phosphorus and carbon content in different organisms. And I don't know if you, the range here, these are autotrophs, and these are sort of atomic C to P ratios. Remember the good old molecular ratio at 106. And we see that there's a huge variability. And the variability is, of course, greater for terrestrial plants than for aquatic plants due to structural tissues and sort of the competition for stretching again towards the light and shading out your competitors. But still, sort of, at least one order of magnitude variability. Well, if we look at herbivores, beetles and other bugs, crustaceans, whatever, then the variability is quite a bit less, sort of like a factor of 4. Which maybe says something essential about the contrast between being a metazoan, a motile metazoan, versus a sedentary, either multicellular or unicellular plant. That there is a huge plasticity in autotrophs compared to consumers. So maybe we could even say that if we're going to take this to the extreme, say that metazoan herbivores are homeostatic. They consist of cells that are organized in tissues, and the tissues communicate to circulating systems and hormonal systems and neural systems and things like that. So it says sort of, stop liver, don't do this, don't accumulate so much lipid, I can't take it, or at least it should say. While autotrophs don't necessarily have that same constraint. And that creates some possibilities and opportunities. That, for example, you can't take 1 gram of plant material and convert that to, let's say, okay, you have to have, I mean, the second law of thermodynamics demands that there has to be an overhead, but usually you can't convert that into consumer biomass without something being in excess. So there's a mismatch. There could be a mismatch between the stoichiometry of the consumer and the stoichiometry of the consumer. And it could even lead to something that was considered a bit theoretical at that time, that secondary producers could actually be limited by things other than carbon or energy. That you could, for example, conceive the possibility of having a phosphorus limited daphne, which is something that we, I think, have proven or shown quite convincingly that is indeed possible. So this is sort of the backdrop of this. Let's say that we now have a system with plastic autotrophs with variable stoichiometry and homeostatic consumers. What would be the consequences of such a system? Would there be any consequences? Would it just not matter? Well, one way of finding out is, well, we can go back to Lotka again and find inspiration. Lotka was thinking, of course, a lot about this, and that's one of the reasons why his name is attached to this Lotka-Volterra equation system that every textbook in ecology usually says something about. Something that is important in this context here, and it sort of has to do with that people who analyze dynamical systems, they count sort of like the most primitive human tribes on the planet, sort of 1, 2, many. Anything beyond, if you have 3 or 13, is not really that important. Because if you go from 2-dimensional systems to 3-dimensional systems, then there is a sort of Pandora's box of all kinds of dynamical menagerie that opens. Then you can have dynamical chaos and deterministic chaos and things like that. If you stay in the plane, then simply because the sort of existence proofs or existence definitions of solutions of differential equations, then you by definition can not have trajectories, solution trajectories that intersect. Which means that the repertoire of dynamics is indeed very limited compared to if you have more than 2 dimensions. Basically, as Lotka pointed out, you have things like you can have cycles of various kinds, you can have attractors, you can have repellers, and you can have various combinations of that, but that's basically all. Which means that there's, and again, those who remember the Ecology 101 textbooks know that there is a lot of things you can do just by looking at graphs instead of doing scary, tedious eigenvalue analysis and things like that. So now I'm going to try to lead you through step by step. It's a sort of plug-in approach, I think we can call it. And the first step is from Lotka, so it's from 1925 to 1971, or maybe no, actually. This Rosenzweig-McArthur model was published in the late 60s, but the most famous paper is from 1971. So again, we have 2 differential equations for x, which we will call autotroph or producer biomass in, for example, carbon units. And we have y, which is consumer biomass in, for example, also carbon units. And these are related through the dynamics, and each of the dynamical equations consists of 2 terms. It's a sort of a gain and a loss term. The gain term for the autotrophs is proportional to something to a growth rate, and the loss is proportional to consumption rate times the biomass of consumers. Notice also that we formulate this capital D here is like a dilution rate, so it's sort of like this Q in, Q out that Babel was showing. It sort of means that this is an open in-out system. Think of it as a dilution culture or something like that. But you could also think of it as a basin of some kind. For the consumers, you also have a gain and a loss term. And the gain, both the gain and the loss are proportional to the consumer biomass. And this G is basically the what we usually call the, I mean, in the classical literature we often call this the functional response of the consumer and this the numerical response. So this is the amount of prey eaten per consumer per unit time, and this is the conversion of this eaten prey into consumer biomass. Is this okay? Is it? I can go faster, I can go slower. And then the idea is to try to, I mean, this is the classical Lotka-Volterra system. So we can say that, well, if the specific growth rate is just a constant, and if the consumption rate is also linear, sort of what we usually call Holding type 1 functional response, then we get the classical Lotka-Volterra equation system. And moreover, we find that this equation here is 0 if y is equal to k minus d divided by I. So that means that the null climb for the autotrophs is just a horizontal line. It's the amount of consumers you need for the consumers to eat producers faster than they can reproduce. And equally, we can, the same ways, we can solve this equation for dy dt equals 0, and then we get this vertical red line, which is the null climb of the consumer, saying basically that if you have a prey biomass that is higher, that is on this side, then the consumers will grow, and if you're on this side, then they will decline. Enough food, not enough food. This is pretty basic. And then we have two modifications that we can play with. We can either include density dependence in the functional response, sort of go from Holding type 1 to Holding type 2. In other words, that the consumers become less efficient in capturing the prey, the more prey there are, because it saturates. The poor consumer is so occupied with processing whatever he has found that he can't really do anything. On the other hand, we can also introduce density dependent in the consumer, simply saying that, well, we don't think that the specific growth rate is constant. We think it's a decreasing function of producer biomass. And usually in the textbooks you see this parameterized by something that should maybe be K. And it's usually called carrying capacity. Here we use a slightly different parameterization, and we say that the carrying capacity, well, the carrying capacity is how much X you can get if you take all the nutrient in the system and sort of convert it into biomass through the stoichiometric minimum content. So this is the maximum amount you can squeeze out from a certain amount of nutrient. But otherwise, this is simply the logistic equation, Verhulst's logistic equation from late 19th century. And of course, these two modifications, they have radically different consequences. Because what happens if we plug in the saturating functional response? Well, what happens first of all is that the consumers become less and less efficient the more biomass, prey biomass there are. So it means that you need more and more consumer to keep the biomass in check. So that means that the null climb, the prey null climb will no longer be a horizontal line, but it will sort of bend upwards. And the consequence of this, since there is no carrying capacity, is that both prey and consumers go to infinity. Pretty stupid model. But it's sort of showing the destabilizing effect of the type 2 response. On the other hand, if we plug in the logistic density dependence, then we bend the producer null line the other way around. So it eventually intersects the x-axis at some point here, which will be sort of the characteristic. And then you may have started wondering, but shouldn't that be a straight line? And the reason is, if you look at the axis here, you see that there is not equal intervals between the numbers. So this axis system is square root transformed. Square roots are nice because you can still have zeros, but you sort of still compress the large numbers and expand the small ones. So it's nice to have this square root scale for dynamics that can go from very small to very large, but it has this slightly annoying side effect of making straight lines into parabolas. We have to live with that. And what MacArthur and Rosenzweig then did was, of course, to combine both of these effects. And what you get then is that you sort of first you get the destabilizing effect of the saturating functional response, and then you get the stabilizing effect of the carrying capacity. So you get what was called in one of their classical papers a prey isocline with a hump. And this hump and the position of this hump in relation to the consumer isocline has critical consequences for the stability. So if this intersection is such that you have a negative slope on the green line, then it's locally stable. If you have a positive slope, then it's locally unstable. And when this equilibrium is unstable, you get the limits. That was 1971. And then we fast forward a little bit more, sort of to maybe mid-90s, where we try to modify this slightly a bit more. Again, the same sort of plug-in approach. We recognize the old sort of logistic density dependence. And then we have a variant of that where we simply have taken into account what Lotka told us. That the consumers and the prey are basically made of the same stuff. So it means that if you take some of the total nutrient to make consumer biomass, well, then there will be less available to make producer biomass. So what we have done is nothing but sort of subtracting the amount of nutrient bound in the consumers. And remember again, we assume that the consumers are homeostatic. They have a constant element content. So this is just a constant multiplied by the dynamic variable, which is the consumer biomass. But we subtract that. So that means that we now don't have a constant carrying capacity, but we have a carrying capacity that varies inversely with the amount of consumer biomass. That always happens. Can you imagine that there is a line that goes like this, which shades in gray the area there? It actually follows more or less that green curve. So, because now that we have introduced this stoichiometric constraint that affects both producers and consumers, it means that we have constrained the whole system according to Lotka's equation. that the total nutrient has to be larger or equal to the consumer biomass times its constant nutrient content plus the producer biomass times its minimal allowable nutrient content. So that means that, and this is sort of, well, you can find this idea in many different models, but it basically says that there are some parts of what you need to make an organism that are non-negotiable, minimum amount, and there are some extra that you can fit in addition to that. And for some nutrients, for example phosphorus, we know that a lot of autotrophs have a lot of storage capacity. They can store sort of several times their immediate need in various ways. The other thing, so we say that, okay, we have that the consumers have a nutrient content that is Q, and we have autotrophs that have a nutrient content which is equal to NT minus QY divided by X. And that means that the stoichiometry between producer and consumer can vary. But if we are going to make consumer biomass with a constant stoichiometry out of food which is allowed to vary in stoichiometry, we need some mechanisms to balance the books. And the simplest possible way of balancing the books is to say that, well, if the prey has more nutrients than the consumer, then we don't care. Then we just do the books in carbon units and don't care. The whatever excess there was in the food is just sort of implicitly assumed to be recycled instantaneously. On the other hand, if the prey contains less nutrient than a unit of consumer biomass, then we have to reduce the growth efficiency of the consumer to make things happen. And we do that by simply, this is sort of disguised, let's say the N minus QY divided by X is actually the nutrient content of the prey. So it's the ratio of the nutrient content of the prey to the nutrient content of the consumer. If that ratio is larger than 1, then we don't care. If it's less than 1, then for example 0.5, well, then you can't have a growth efficiency that is higher than 0.5. So we have to reduce. So that means that we have two stoichiometric effects that we need to try to introduce here. It's this all is made of the same stuff kind of effect, and it's the stoichiometric balancing or variable conversion efficiency effect. Again, if we start with the Mercator-Rosenzweig model, then we see that we have where the isoplines intersect, we have an equilibrium. And in this case here, this equilibrium is not locally stable, so we get the limit cycle. If we now plug in the sort of stoichiometric effect, the variable carrying capacity, we turn this limit cycling system into a stable focus. But still, because we have only done sort of half the story, still the dynamics goes half the time outside the area that it's supposed to stay within, because we haven't done both of the things we need to do to constrain the composition of the consumer. If we, on the other hand, do just the sort of effect on conversion efficiency, but not the effect on the carrying capacity. Yeah. See again. What happens here is that we go from a prey isocline with a hump to a prey isocline without a hump. That is sort of the stabilizing mechanism of the stoichiometric constraint. If we, on the other hand, just introduce the conversion efficiency constraint, then nothing happens with the prey isocline, while the main effect is that now the consumer isocline also will have a hump. It will no longer be just a straight line, it will be a hump, and it will even intersect the x-axis at some point, which is the point where the prey is so poor in nutrients that it is not possible for the consumer to maintain positive net growth rate. So it's sort of really limited by the nutrient content of the prey. And if we combine those two, so that we both get rid of the hump on the prey isocline, and we get the consumer isocline with the hump, then we see the very strong stabilizing effect of the stoichiometric constraints. So the way we have formulated these equations are such that we sort of have a number of parameters that are, let's say, properties of the organisms, sort of how much they can eat, how much nutrient you need to make, and so on. And two parameters that are obviously things that we as experimenters can manipulate, or that could vary due to sort of physical properties of the system. It's the dilution rate or the true flow rate, and it's the total nutrient. So then it becomes interesting to try to look at what happens if we turn these two knobs. And then again we can sort of look at this as a 2x2 system. Low dilution rate, high dilution rate, low nutrient, high nutrient. And what basically happens is that if we have low nutrient, low dilution rate, we get intersection of the isoclines with the sort of negative slope and things like that, and we have internal focus that is being attracted without any overdamping. So there's no oscillation around, it just goes bang onto the target. On the other hand, if we turn up the dilution rate, then the sort of dilution losses affect the consumers more than it affects the producers. So there's not much change in the producer null-climb, while the main effect on the consumer null-climb is that it sort of shrinks. And it shrinks to a situation where they no longer intersect, which means that the only possible solution is the intersection between the autotroph null-climb and a situation with no consumers, deterministic extinction of the consumer. On the other hand, if you have high nutrient, then the prey isocline will have a hump, which means that we can also have sort of Rosenzweig's paradox of enrichment that he said, and that this was published in Nature in Science in 1971, that humans should be careful with fertilizing exploitation systems, because that may have destabilizing effects, and that may be that you would, by that, would actually exterminate the product or the whatever you would be interested in harvesting. So, and of course, what Rosenzweig swept under the carpet is that this type of dynamics, limit cycle, is in principle locally or globally dynamically stable. It means that if you start at any sort of valid starting point, then the system will go here and nowhere else. And of course, he was pretty sort of out of his hat, some sort of demographic stochasticity, because sometimes you get very low, down to very low abundances and things like that. But in principle, you don't have deterministic extinction in the classical Mercator-Rosenzweig system. On the other hand, if you have deterministic, if you have stoichiometric constraints, then you can have deterministic extinction of the consumer under certain combinations of fertilization and manipulation of loss rates. Maybe I can try to show something. This is something I coded so long time ago. I hardly ever use MATLAB anymore, so I've almost forgotten how I actually made this. But it's basically, well, again, there's a gray shadow that doesn't want to show up. But we have the consumer isocline and the producer isocline. And we can, for example, play around with these sliders and see how the isoclines change. And if we go sufficiently...
What are you moving now? Sorry.
I'm moving this slider, which is the total nutrient.
Okay.
And then I can move this slider, which is the dilution. And then, for example, I can start the simulation. See if I can do it. Let's say.
Sorry, I didn't get what the blue line was.
The blue line is now, the blue line, which is coming now, is that I'm starting a simulation from this particular point. And I'm just continuing the simulation until oblivion. So this is a situation where this exploitation system collapses because the food eventually becomes so poor that it's just junk. It's sort of going to McDonald's every day for every possible meal, kind of thing. If, on the other hand, we on the other hand, we turn the dilution down, then we get the tiny little limit cycle around this equilibrium point. And if we, let's say if we start from some other point, I don't know. It's sort of just trying to illustrate the dynamics you get around these equilibrium points and how the dynamics change when you simply change the geometry of the null lines. Yeah, as I said, this I'm not really sure.
Tom, sorry,
Yeah.
just a quick question. If you started somewhere outside, somewhere right up corner, do you get into the same equilibrium point?
No, again, it's let's say the color gamut of the projector should have shown that the allowable area.
Okay.
So this line that sort of represents producers at their minimum nutrient content goes more or less here. So I can't start here because then I would violate sort of I would start with algae that had less nutrients than the minimum allowable content. And this part of the geometry is also what makes stoichiometry such a strong constraint on dynamics, because it sort of confines the dynamics within or bioconservation, basically. So then we can.
Sorry, the dilution rate, can you maybe go over that again?
Yeah, I mean, it's basically such that you have some volume and you have water without organisms, with sort of fresh medium or terrestrial runoff or deep water upwelling or something like that coming in here, and you lose the same amount of volume, for example, through the Kattegat or something like that. So it's basically a dilution rate. And I think one of the main points is that this dilution so much harder than the producer, because in a system like this there is sort of no harvesting, so that the equilibrium will always be such that the growth rate of the consumer is very low, and that means that a small change in the dilution rate can make a big difference for these guys, but not really for these guys. So again, we can go through this systematically and sort of turn this dilution and total nutrient loads like this. And by doing such an exercise, we have actually then produced what we would call a two-dimensional or co-dimension 2 bifurcation diagram. It says that we have a total nutrient concentration and we have a dilution rate, which means that every point in this plane sort of corresponds to, let's say, one particular physical system or one particular experimental condition. And just by finding out where we are in the plane, we can say something about what will come out of this. So if we are here, for example, we will have coexistence of herbivore and autotroph in a stable focus. If we are here, they will still persist in a limit cycle. But if we are outside the blue line, then the herbivore will eventually be extinct, because eventually the nutritional quality of the food will become so bad that they cannot survive on it. And if we, for example, choose one particular nutrient concentration and turn up the dilution rate, then we see that we go from cycling to stable focus to extinction. So we have sort of cycling, focus, extinction type cascade. And this type of bifurcation analysis is something we will sort of return to in various incarnations. But it's for this simple system here, you can basically solve for these lines simply by solving a set of nonlinear equations which are actually related to the determinant and the trace of the Jacobian matrix. We'll get back to that. So let's play a little bit longer and say that, okay, let's now introduce the good old carrying capacity again, but in terms of something that affects the autotrophs only. For example, the available CO2 or available light or something like that. So it means that instead of just having to subtract the part of the total nutrient that is located in the consumer, we now have the situation where there are two possibilities for the autotroph. Either that it can be nutrient limited or that it can be limited by something else. And the main effect of this is that we then truncate the autotroph node line such that at some point when this hump curve reaches the carrying capacity, it just falls vertically to zero. Which again, and this is, I guess, something that mathematically inclined people like to play with, is that we make new possibilities of multiple intersections between the isoclines. And multiple intersections could mean things like bistability or stability shifts and sort of, well, catastrophic changes in dynamics. So there was a dude from Georgia in the, not Georgia on my mind, but Georgia in the good old Soviet Union, Irakli Lolatse, who did his PhD with Jim Elser and some real, he's a real mathematician. He played around with this variant of the stoichiometric model, where you also would have a carrying capacity for the autotroph. And then he produced a bifurcation diagram, which is slightly more complex than the one I showed you previously, and which also introduces some new concepts that we will return to. First of all, I mean, this is the x-axis here is then carrying capacity of the autotroph. So it means, for example, that we increase the PCO2 or something like that in the system. And it shows the equilibrium consumer biomass. So it basically shows that for a certain low amount of total carbon, you will not have enough production to be able to support the second trophic level. But as soon as you pass this critical level, the consumer biomass will increase. And that type of sort of sharp change in this type of diagram is what we call, first of all, we call all these branching points for bifurcations. They represent points where the dynamics change in a qualitative sense. And this type of bifurcation is what we usually call a transcritical bifurcation. It's a smooth bifurcation in the sense that you have curves that are connected. They are continuous. They are not continuously differentiable, but they are continuous. And turning the K knob further, we get to a point where we have a stability loss through something that is usually called a Hopf bifurcation. Technically is when you have a pair of complex conjugate eigenvalues in the Jacobian matrix where the positive or the real part crosses over to the positive part of the axis, real axis. But it means that instead of going to a stable focus, you go into a limit cycle of some sort. And then, turning the knob further, there is something new happening. And this is another type of stability exchange. It's a very general stability exchange mechanism that we call a saddle node bifurcation. It's basically when two different types of equilibria collide and either annihilate each other, or they exchange stability. So this means that this oscillation is collapsing into a stable focus again. And then, as you increase the carrying capacity of the autotroph, the amount of consumer biomass, the amount of zooplankton biomass goes down. And it goes down because the food quality becomes poorer and poorer, and again to the point where the food quality is so poor that the consumer cannot persist. So then again we get sort of a new transcritical bifurcation to extinction. And well, Jim Elsa is also one of the co-authors of this paper, and Jim is pretty good at. He should probably have been a used car salesman in another life. So this thing here was then coined the paradox of energy enrichment. You sort of increase the energy input to a system with the effect of maybe sort of destroying the production of something you would be interested in. Yeah. And all of these models that we have looked at so far, they have in common that they use a minimum function. Just as Bertrand was showing, and I mean, they are bound. They are sort of related to this German chemist from the 18th century. He, I think I read someplace that he wrote down or formulated something like 150 different laws of how things behave in nature, especially in agricultural systems. But for some reason it was only one of them that survived the, what do you call it, the tooth of time or something like that. And that is what we today call Liebig's principle of the minimum. And he had this nice analogy. I mean, in the days when you still used barrels to put store stuff in, that you had a barrel with a number of staves with unequal length, and then the water level in the barrel would then be determined by the shortest stave, which is something that we in mathematical terms often translate to using a minimum function. There are certain things that are, I mean, minimum functions are nice in the sense that they sort of, I mean, they sort of convey a principle that is generally accepted It's easy even for people who are not really good programmers to use this function. But it has certain very undesirable properties also. One of the most important properties is that, well, we have said that in sort of bifurcation analysis, you can sort of say something very specific qualitatively about the behavior of the system, but just looking at its local behavior around equilibrium point. And that is, in a sense, true, and in a sense, not. It's true if the dynamics are smooth. And by smooth, I mean continuously differentiable. And the minimum function is very often continuous, but it's not continuously differentiable.
Can I just ask something? For the previous plot.
Yeah.
So we're looking at a closed system.
Yeah, I think this model is formulated. This is like a closed system, yeah. But
Because I cannot put that in reality. I mean, yeah.
But
I have trouble understanding what it
let's say
implies.
the previous versions were all open systems in the sense that you had a sort of input-output relationship. But I think this is formulated such that it is closed, and it's sort of what mathematicians do, because they, I mean, he's doing sort of existence and boundedness lemmas for solutions and stuff like that. So it's sort of pretty technical compared to what I'm capable of doing. But I mean, I mean, for example, this is an open system where we directly use the openness as a determinant of the quality dynamics.
Because I have a problem understanding how, when there's decay, there's going to be decay of producers or, well, no, of consumers. They aren't going to release their nutrients, and then it's going to go back in the system.
Well, there's a loss rate. It's sort of like, I mean, basically that this, which is some kind of combined mortality and respiration rate, and that sort of when zooplankton dies, it says poof, and it sort of returns to its constituent elements, which is, well, obviously a simplification. Yeah, so I mean, one thing is that you need to invoke pretty much more complicated ways of analyzing stability during bifurcation analysis if you have kinks, or sort of these points here are all minimum functions. So it means that this curve is continuous in the sense that if you start from here and go there, and if you start from here and go there, they end in the same point. But the derivative from this side is not equal to the derivative from that side, so it's not smooth. And smoothness is something that all differential equation solvers somehow utilize, because a differential equation solver uses the dynamics to look ahead. How are we going? Are we going up or down? Are we going up or down fast or slow? Can we take a large leap, or should we take a very small leap, small step? All this is something that happens behind the scenes if you use some of the classic ODE solvers like LSOD or whatever the names are, RK45 in MATLAB or whatever. So there are sort of both, let's say, logistical and theoretical reasons for questioning the kind of let's say, heuristics that we can construct with the help of minimum functions. And the question is, are there alternatives? And then we say, I guess, meanwhile, in Amsterdam, this guy here had been sitting for 10, 15 years and sort of pondering on, I think he says it started out with that his boss came to him with some Daphnia toxicity data where there was something that was increasing on the x-axis and number of dead Daphnia was sort of increasing. And if he could find a way to draw a smooth curve through those dots. 10 years later, Buzz Hoyman came out with the first version of the book called Dynamical Energy Budgets, which is basically, it's an extremely ambitious project, and I mean, it's in a sense controversial. There are people, it's almost like religion to some people, and I mean, there's also people who obviously hate this guy almost religiously. So, but it's an attempt to find a way to represent living things in the most general possible way based on first principles. Sort of not heuristics, but sort of try to build some kind of logic of how living systems function. and the main vehicle for the whole depth theory is basically saying that all living organisms are, in an abstract sense, made of two kinds of stuff. And he calls one kind for structure and the other for reserve. And that doesn't mean that reserve is fat. It's more subtle than that. But there are rules. For example, that you can make structure out of reserve, but you cannot make reserve out of structure. And so on. And one of the things he developed, this was published in '98, and it was sort of about this thing with how can you assemble something from two or more building blocks. And what he noticed is that, of course, there is a huge theory in stochastic queuing theory, which says something about when you have things that arrive at different rates but should be combined in various ways. And it's things that theories that are used in, for example, manufacturing and sort of how many counters you should have in a supermarket and stuff like that. And the idea is really simple in the sense that, let's say, if we have a reaction of the type, we need one A and one B to make one C. And we assume that A and B arrive at some things that some place that he calls a synthesizing unit, and that they arrive as Poisson processes, which means that they are sort of independently time increment probabilities. So, for example, here you see the black dot, then one B arrives. The B sits there, nothing happens. Until an A arrives. And then you have A and B and can make a C. And you also notice that in the meantime another B arrived, but that couldn't do anything because the binding site was already occupied, so it was rejected. And then the process starts over again. This time A arrived first, and then a B, and then we got produced a C while an A was rejected. The actual theory here, where this is pretty, it's over my head, but the consequence, this sort of something I can handle.
Can I just ask something else about
Yeah.
this schematics? If it's mechanism and kinetics, why would there be difference in time before B and A creates C? Because if it's same B and same A for the first kind of shape,
Yeah, but I mean, I think the argument would be the same if you sort of shrunk this to zero. But I guess that on a certain time scale, the actual, let's say, if you have an enzyme where you need two molecules to sit in two specific reactive sites, then the actual reaction, where, for example, the enzyme twists or breaks or does something, it takes some finite time.
Yeah, it's going to be the same. I mean,
yeah.
At the time when the second substrate has arrived, so or did I see badly?
No,
Is it similar
I think you make a good point.
Okay.
And it seems like there here is, I don't know what the details are, but I would imagine there is a distribution of conversion times instead of a sort of fixed conversion time. I would imagine. Good. So if we compare, let's say, this type of minimum functions that we often have, we have like two Monod curves or rectangular parabolas or something like that, and we chose the one that is smallest. And the synthesizing unit of this would be written something like that. And we notice that this type of Monod expression can also be written as something like that, if we want to do it in a complicated way. 1 plus 1 over x inverted. So there's sort of some likeness in the sense that this part here is actually the same as this, but then you subtract something which I guess is due to this sort of rejection probability. And then I've just drawn the level curves here of the red is the synthesizing unit and the dotted is the minimum function. And you see that the synthesizing unit does a pretty damn good job of mimicking the minimum function while at the same time being a smooth function when you are close to zero. It does a worse and worse job as far the further out you get, but then again in the, let's say in the marginal of it, when we, especially if we go further out on the axis, we sort of recover the Michaelis-Menten function. So if you let x or y go to infinity, let's say you let y go to infinity, then you have 1 over infinity minus 1 over x plus infinity, which both of these terms disappear, and you get back sort of the good old mono or rectangular. So Maria asked me to suggest some papers to read. Lotka-Volterra, he did his PhD with Bas Koyman and some other guys that I think I will introduce after a while. Has anybody tried to read that paper? Did you think it was easy read?
It's a few comments.
I think I printed it.
It's demanding stuff.
Yeah.
But I mean, it's also so that going from 2 differential equations with very simple heuristics, and then to 10 differential equations when you try to do this properly. So it means that you have now, because well, each the organism, the abstract organisms, is sort of split between structure and reserve. But if you want to have both carbon and nitrogen limitation, then you need to have two reserves, one for carbon and one for nitrogen. Or actually it's such that the autotrophs have carbon and nitrogen reserves, which you could maybe connect with the carbon reserve would be the chloroplasts and the starch storage system and things like that, while the end reserve would be associated with alpha-ketoglutaric acid transamination or something like that. Sort of the basic ammonia assimilation or nitrate reduction machinery, plus reducing energy and all the stuff that you need for that. While in the herbivores you would say that the CNN reserves would be more sort of like carbohydrates and proteins mainly.
Is it still assumed that they are in homeostasis?
Yeah, let's say the big difference between Deb and let's say the kind of heuristics that I've been showing here is that, yeah, homeostasis applies to each of the components, but the amount of C and N reserves and structure per organism can vary. So it means that we have now sort of departed from this consumer homeostasis condition. And also, I mean, what the heck? When you anyway have 8 differential equations, why not throw in 10? Doesn't really matter, does it? So it also means that there is some, let's say, slow recycling of excess substances from the consumers in terms of the trital carbohydrate and protein. And yeah, in a sense, I mean, this is pretty heavy stuff, but since the equations are smooth, then there are actually good pieces of software out that can do more or less this bifurcation analysis for you if you have the skills to sort of handle that software. There are several products. I think these guys use something called Acto, which has been around for 20 years or something like that, but there are also other alternatives, including, for example, for MATLAB, there is a toolbox called MatCont, which allows you to do quite a number of bifurcation analysis. And I won't say very much about this, except that the basic idea is that what we see again is this, well, the transcritical bifurcation, simply meaning that at a certain amount of total nitrogen, there is enough production that you can sustain the second profit level. And then if you turn it up further, then the system will destabilize, and it will destabilize through a Hopf bifurcation. And then this destabilization can happen in different ways. But sort of in broad terms, the same pattern. So, I mean, there's certainly something to recommend about that way of doing things, but there is certainly also a substantial overhead in trying to do the books properly in this kind of representation.
Should we go for a short break?
Yeah. Initial confrontation here, I could say death match between Liebig and Deb, and you would say, should I care? Does that really mean anything? There's an interesting example in about 2002, maybe. a guy in the Netherlands that I really respect extremely highly, Jeff Huysman, wrote a paper in Nature together with another guy, Frans Weissing, concluding that you could have 6 species of phytoplankton coexisting on 9 limiting resources if they were competing in chaotic dynamics, which sort of, well, in a sense, violates competitive exclusion principle, although it has sort of been known for a long time that competitive exclusion is basically strictly valid only in a constant environment. But this exercise where they had, let's say, I can't remember exactly, but maybe let's say 6 species of phytoplankton competing for seven or 4 limited resources or something like that. So you had more coexisting species than you had limiting resources. And the formulation of this model was quite a good old minimum function. Same as we were shown earlier today. And what, of course, Bas Koyman did when he read this paper in Nature was that he went home and wrote the same model, but using synthesizing units instead of the minimum function. And lo and behold, then the coexistence of more species than limiting resources didn't hold up. So the whole conclusion, which is being celebrated and sort of it's probably in the textbooks these days, is simply not structurally stable because of this, let's say, the lack of structural stability in minimum functions, I think you could say. The lack of smoothness means lack of structural stability. So we have this conflict, so to say, that when amateurs like myself and many others try to model, we use simple heuristics, and we like to use things like the minimum function and things like that, because that makes things simple. But it is, in a sense, a heuristic, and it's maybe not a good heuristic even, or at least with side effects. There is not the only way of doing smooth dynamics, but it's at least, it's a way of doing it that is getting, let's say, I think we could say increasing following, and not the least because University of Amsterdam, or Free University of Amsterdam, has been very good at arranging these online courses in depth theory every year, and they have, for some of you who are PhD students and looking for some extra credits, maybe not the easiest credits you can find on the planet, but interesting, then you should really check out this depth course. So then the question is, can we compare these apples and bananas, or whatever we could call it? And I think up to recently, the answer would be, that's pretty hard. And then, maybe in the last 5 years or so, there has been some really interesting developments, and it's sort of driven by the general interest in systems biology and sort of large-scale computation with biological systems, and especially how physicists have been catching interest in the kind of computational problems that you run into when you have huge systems of nonlinear differential equations. For example, metabolic systems. So, generalized dynamics is one word they use for this. And this thing I will say now is, I have this guy here, I think he did his PhD at the University of Wittenberg. but he is definitely, I mean, there's also another guy, for example, on this paper, a guy called Bob Coy, who is from Koymann's group in the Free University of Amsterdam, and there's also some physics guy, this Thilo Gross, I think his name is. Anyway, this is something we, in a sense, recognize. It's sort of the two differential equations that we started with: X, autotroph biomass, Y, consumer biomass, and we have some function S, which describes the production of X as function of X and Y. So it means that we can incorporate both density dependence and stoichiometric effects on the production rate of the autotrophs. And then we have a more sort of simple univariate function, which is the functional response of the consumer, which is then, as before, production minus consumption loss. And the mass balance of the consumer is the numerical response minus some mortality loss. So just remind you that this D that turns up here is not really exactly the same as the dilution rate I talked about earlier in this sort of open system formulation. And the numerical response is equal to the functional response times conversion efficiency. And again, we assume that the conversion efficiency depends on both X and Y. But otherwise, we haven't really said anything about how the nature of this function S, F, and E. So the basic line of proceeding here is, I mean, it's probably as mathematicians like to do, that you want to get from something that is, let's say, milligrams of carbon per cubic meter or something like that, to something that has nice dimensionless units. And let's say that there is a solution to this system so that dx dt is 0 if x is equal to x star, and the same for y, so that there is a y star. There is an equilibrium. And then the idea is to say that we don't, not only we define a new variable, which is basically the old capital X scaled by the equilibrium, but we also introduce scaled functions. So we have little s that is a scaled version of the original s, and its arguments are now in the scaled state variables. And since x star is a steady state solution, it means that s star minus f star times y star must be 0. In other words, that we can take that this factor is equal to this factor, which means that we have a common factor that we can put outside the parenthesis, and this common factor can be interpreted like turnover rate of the biomass. It's sort of reaction time constant of that variable. And then the last step is simply to say that we don't really we want biological time, we don't really need clock time. So we rescale the time in terms of generation times of the producer or something like that. Which means that we end up rescaling this parameter to just having one, this equation set to just having one parameter, which is the ratio of the turnover times of the autotroph and the producer. Otherwise, it's so that if x and y equals 1, then we have a equilibrium, and also that this function s, f, and e, they have value 1 at this equilibrium point. So then is the question, what can we get more from this? Well, we have an equilibrium point, and the local stability around that equilibrium point is determined by the eigenvalues of the Jacobian matrix of the dynamics. And the Jacobian is basically the partial derivatives of the dynamics. So it's sort of related to what we looked at when we looked at the isoclines, at the classical Rosenzweig-McArthur model, sort of whether the prey isocline had the positive slope or a negative slope at the intersection, that would be equal to the partial derivative of the production versus producer biomass. So it means that the Jacobian for this two-dimensional system is sort of simple because it's just a 2x2 matrix. It's the derivative of s with respect to x minus the derivative of f with respect to x. The derivative of s with respect to y minus the derivative of y with respect to y. And so on. There's some other thing that is very important to realize with this rescaling, and that is that these partial derivatives, if we transform them back to the unscaled functions, we see that, for example, this sigma x is the partial derivative of s divided by s star times x star. And what does that mean? Well, it means that it says something about the relative change in s for a unit relative change in x. Or we could also have written this as the partial derivative of log s with respect to log x. But this is what especially economists, I think, are sort of using this type of notation very much, and they call this elasticity. And it sort of says something about the return rate of something. So if you have an elasticity of 1, then that means that you have a linear relationship. You have a one-to-one relationship. If you have an elasticity of 0, then it means that you have a constant. And if you have an elasticity of 2, then it means that you have a parabolic sort of second-order relationship. Which again means that elasticity of 2 means 2-unit change, a doubling of x gives a quadrupling of s. And how can that be relevant? Well, it actually is in some some of the classical functional responses. Remember the Holling type tree response, where you have sort of where you don't have a linear relationship between consumption and prey density at low prey density, but you have a second order. That exactly translates to this gamma having a value close to 2. And we know maybe from various other places that the type tree response is a very strongly stabilizing part of prey-predator dynamics. So, yeah. So what they then do, and this is mind-blowing in a sense, but they do something really cool. And that is that they now are able to, I think earlier we looked at the two-dimensional bifurcation diagram, where we could say something about how we turn two knobs, and then we could get dynamics that would either be persistent or stable focus or some kind of destabilizing. Here they are actually able to analyze 3 different properties of this system, and they are even able to analyze it in very, general terms, because they put very interesting interpretations on these partial derivatives. And actually the original elements of the Jacobian were called sigma and ni. And then they find out that, well, it's actually these parameters can be rescaled in an interesting way, so that their domains go from 0 to 1. And such that this C parameter is the degree of intraspecific competition. So it's sort of the, I think, like a carrying capacity axis. And the gamma, that's the sort of the slope of the functional response at the equilibrium, which can go from 2, which would be a type 3 functional response close to the origin, and all the way down to 0, which would be a type 2 or type 3 functional response at the plateau part. So the part where there is absolutely no change in feeding rate by changing the amount of prey. And finally, the stoichiometric effect on prey conversion efficiency is on this axis here. So running from 1 being sort of equal to no stoichiometric constraint on numerical response, and down to 0, which would mean a very high stoichiometric effect. So now we have sort of these 3 axes, and then we have a volume. And it's a volume with sort of, well, it's 2 units large. 1 by 1 by 2. And the top part of this volume represents situations which are locally stable. So it means that if we are anywhere in this volume above the red or the blue plane, we have a locally stable, or globally asymptotically stable system with the focus. If we are below the red plane, then we have stability loss in terms of Hopf bifurcation, so that it means that we have a limit cycle, some kind of oscillatory. And then finally, the blue is this transcritical bifurcation, which is sort of this paradox of energy enrichment type thing, where you somehow you have that the system loses stability and is destroyed typically by the consumer going extinct. And it means that, for example, if we are here, then we have a model with no stoichiometric constraints. And it simply says that as long as the carrying capacity is sufficiently low, we have a stable focus, and at some point we get a Hopf bifurcation destabilization. And the blue plane is going exactly through the axis, so it is no possibility of getting deterministic extinction when there's no stoichiometric effect. if we go this way here, it means that we sort of increase the stoichiometric constraint on conversion efficiency. And it basically means that, first of all, that this extinction through a transcritical bifurcation appears, and also that the destabilization, the sort of Rosenzweig's big argument with the paradox of enrichment in 1971, also disappeared if the stoichiometric constraint on the consumer is sufficiently so. So that's a pretty impressive story to be able to tell in extremely general terms by just these two planes and how they intersect. So now we can go back to, if you remember the Lotka-Volterra model from 2000, where we had this transcritical bifurcation, the paradox of energy and enrichment. What Stiefs and co-workers do is to make sort of a smooth version of this model. It's not really dead, but it sort of replaces all the minimum functions with synthesizing unit type functions. And you see that it's sort of encouraging that mostly the dynamics are similar. We have the same two transcritical bifurcations, and we have some details that are different in especially how these attractors collide in the saddle node bifurcation. And if we look at this volume from the top, so we don't really care about the gamma, the sort of sensitivity to the functional response, then we see sort of very directly how these two models connect, because the model with the minimum function has basically two modes. Either the producers are limited by something else, that means that we are at this sort of no stoichiometric effect part of the plane, or they are limited by nutrients. And we have two branches, but they do not connect. And the smooth dynamics basically has the same geometry, except that now these two branches are connected in a sort of parabola-like fashion. But so, in one sense, we can say that the smooth and the non-smooth dynamics have qualitatively the same behavior, in the sense that you have the same two qualitative branches, while the details, the differences are in the details of how they are connected. On the other hand, there are also situations where you apparently do not get such direct correspondence, and that's more when you go into sort of, let's say, a more strict dynamical energy budget formulation versus, let's say, more paradox of enrichment type of formulation. And I mean, these two bifurcation diagrams, they don't look too different. I mean, we have a Hopf bifurcation here where a stable focus is sort of rolling out into oscillatory, destabilized into some kind of limit cycle. But the interesting part is on this side, where you have the transcritical bifurcation, where you have a continuous connection between, let's say, consumer not being there and being there, while this transcritical bifurcation is replaced by a saddle node bifurcation in the depth formulation. And this is actually interesting, because what this means is to some extent what I think we in other contexts call an Ali effect. And an Ali effect is an old idea in animal ecology, sort of the idea that you need a minimum number, or minimum population size to be viable. That there's simply too long distance to the next female or something like that when the population is small enough. Or connecting to an interesting experiment that Ulrich Sommer did in 1986, I think, where he showed that he had a system with Daphnia growing on Semidesmus or something like that, and where there was a very sort of sharp difference between, let's say, I can't remember exactly the details, but let's say one run, the dilution rate in this system was 0.2 per day, and in another it was 0.25. And it was only in one of those dilution rates where the Daphnia managed to establish a population. And they established the population by sort of being many enough to graze the prey hard enough that the number of prey became small enough that they could share the available nutrients, in this case phosphorus, in such a way that their nutritional quality became high enough for the consumers to persist. And I mean, Ali effects have turned out to be very important in many other things also. For example, there was a very famous, I'm very excited by this, paper, I think in PNAS, by André de Vos and Lennart Persson and some people in Umeå, so sort of showing that some fish populations where you can have these switches between many small fish or giant cannibals. And much of that dynamic is also through this type of sort of saddle node bifurcations related to an Ali effect, or an implicit Ali effect. Yeah, so I don't know. Rosenzweig's original paradox was, as I mentioned before, it was kind of weak, even though it sort of made the well, it was published in one of the weeklies, and it sort of has become a concept. But the limit cycle that the paradox of enrichment actually leads to is globally asymptotically stable. You can't exterminate a consumer by the paradox of enrichment, while the Lovelace's paradox of energy enrichment can in principle do that. Yeah. So if you want to be remembered, you have to sort of name your own paradox. And Steve said all that did their attempt of sort of turning this coin around. I mean, Rosenzweig said that humans must be careful when they try to fertilize harvestable systems in order to increase harvestable production, because it can backfire. They basically turn it the other way around and say that, well, it's actually so that constraints that may seem to be detrimenting the, let's say, the life of primary producers in ecosystems can actually be positive for the overall stability of the system, which is sort of turning around the alarmist kind of message that Rosenzweig made in his day to something that is maybe more positive. Otherwise, I mean, this Morin and Lawler, that's a pretty sarcastic way of saying it, but and I think it also means that, in the sense that, well, these people who work with this type of modeling these days, they would maybe say that this Hopf bifurcation destabilization is It's maybe not so interesting. It's maybe more a feature of the particular way we represent things than something you would actually go looking for in nature. While the kind of mechanisms that pop up in the terms of transcritical or saddle bifurcations, which are sort of catastrophe mechanisms in various ways, they are probably more relevant and more interesting to start looking for. That somehow systems can be forced into situations where the food for a consumer is so crappy that he can't survive. So we can do some conclusions, which is more or less what I said, and I think that the actual question of how much artifact you can, or how much, not artifact, but let's say idiosyncrasy or special behavior you can create in a model by using non-smooth dynamics is still a bit open. And I would imagine that this is more relevant for models that are in terms of ODEs than sort of 3D partial differential equation models where you have all kinds of approximation and truncation problems in both time and space, and where you would have to be more, I guess, aware of numerical artifacts anyway. But still, this is going to be a very short part. But we can make some observations, and I mean, we can go back, for example. I mean, there is a number of modeling papers that have been, I guess, my favorites through the 80s and 90s. The Steele and Henderson paper in AMNAT, the FASAM nitrogen model. Things don't suck so. I mean, they are actually quite agnostic about whether they talk about P or N in that particular paper, but Fedde has always been a P guy, I think. So, but I think we definitely are in the era of multi-currency modeling. And some of these, some of these have a history back to ERSEM, the European Regional Seas Ecological Model or something like that, which has had a number of descendants and was probably, I think there was a whole industry of EU projects that were sort of developing that, various incarnations of that. And I guess the latest incarnation is this. If anybody have played Quake, then you would know that there's a difference between BFM and BFG. Okay. BFM is the biogeochemical flux model of Vichy et al., which, as far as I understand, is, for example, something that they are looking at Syke for the Baltic Sea.
I think they're actually pretty far. It's like
Yeah. Yeah, I mean, they are definitely running the stuff,
yeah.
And but I mean, it's a yeah, and there could be a long list here. I just mentioned this Medusa, which is I mean, BFM is well, they are running BFM globally, I guess, but it's also being set up for the Baltic Sea. And this Medusa, yeah. So, I mean, just making some cutting and pasting from this Vichy et al. Paper. They make a taxonomy of sort of different living components, non-living organic components, inorganic components, and they are supposed to have a C, N, P, O, etc. stoichiometry. You have the generalized organism here with C, N, P, Si, Fe, vanadium, boron, whatever. And of course, fluxes in and out, photosynthesis, respiration, lysis, digestion, uptake, and so on and so on. This, I mean, it's a really impressive piece of work. And it's interesting that they sort of have tried to structure all these things in a structured way. I don't know. They I mean, there's so many equations in this paper, but this is just 4 arbitrary ones that I snipped out, and sort of more or less. I'm not really even sure what all this means, but I can recognize these max-min functions. And yeah, I mean that's. I think it's really impressive that people manage to stitch together such a big canvas as they do, and it's apparent that the legacy from Justus von Liebig is going strong. So this is Tom Andersen. It's kind of funny. I mean, Tom has almost the same name as me. And he has been co-publishing it together with many of my co-workers. And yeah, he's so much more active in this field these days that I mean, I really like his work. And one of the other papers that I think I gave you to read, which is slightly more transparent, I think. And, he was also a co-author on this Lotka-Volterra. I forgot to make one. I mean, this is just what they basically do in this 2012 paper in this Journal of Marine Systems or something like that, is to just compare one particular piece of 4 different sort of large-scale multi-currency models. Or it's actually 3. This is something that Tom, or I like to call him Thomas, just to not confuse myself, but he hates that. So, well, it's the idea here is basically that you have food that contains carbon and nitrogen, white and gray. And then there is a certain variability in how these different models actually implement the balancing that you need to do in order to make the books. For example, this Alt 95 paper by Andersen and Hessen sort of just subtracts more like gut sorting or something like that. So part of the food is just discarded before it ever enters the animal, and then it's sort of are processed from there. Otherwise, these implementations, they differ, for example, in the way that they make the excretion products dissolved, particulate, inorganic, and so on. So this is just these 4 models, and the y-axis is sort of the fraction of intake of nitrogen and carbon for different food compositions, for different food C/N ratios. So feces, growth, and excretion. And the more or less what all of them have is that when C/N ratio is above some critical level, then growth is determined by N content of the food. But where they differ quite a bit more is what happens with what is left over, especially the carbon. Especially how much of the leftovers that cannot really be converted into zooplankton biomass while conserving mass. You can either have a large amount going to respiration or a large amount going to pellets. And in a situation where I guess these global biogeochemistry models, they have some sort of target that they say that, well, it's not impossible that 50% of the global new production is processed by zooplankton. So it's sort of whether the what comes out of the zooplankton is CO2 or pellets has a sort of, in principle, biogeochemical consequence. So, yeah, I mean, from the times when one of the key papers here was first rejected in 1990, saying that non-energy limitation of growth in zooplankton was the stupidest thing ever said. It was more or less the reviewer comment. To sort of, I don't know if we should say this is mainstream, but it's sort of also coming out of necessity when you have these global circulation or global biogeochemistry models that try to handle multiple currencies in a consistent way. And yeah, Liebig's law is living and breathing. And there is obviously a diversity of how this is actually done. And to some extent, some people would claim that this diversity is due to that it's heuristics that are sort of the there's not really a theory behind how you construct these kinds of models. And I mean, if you want to do some really heavy fine grid computation for the whole planet for hundreds of years and things like that, then you probably need to cut all corners you can. But and as we saw in the other paper, the Kuiper paper, the price is pretty steep if you want to do the books properly. Or I don't know if you should, let's say as some people mean is proper. And I don't know if I can put myself completely behind this, let's say, formulation of my namesake here, but it is, of course, one possible weak point of any global biogeochemistry model, just sort of the actual details of how you choose to do the heuristics of, for example, balancing what comes out of zooplankton in terms of particles versus inorganic substances versus dissolved matter. That was all I wanted to torture you with today.